Beneath the water between England and France lies a railway that changed Europe forever. This is not a tunnel through mountains or solid land. This is a tunnel built under the sea, fighting water pressure every second. Stretching over 50 kilometers, most of it runs directly below the seabed of the English Channel. It is like a submarine mission, but for trains. One mistake down here, and the sea does not forgive. Water pressure is the real enemy. Before digging even 1 meter, Britain and France had to agree on laws, safety rules, and money. 2 countries, 1 tunnel, and no room for error. Engineers knew they could not dig just anywhere. They had to find the perfect underground layer. That layer was chock marl strong, predictable, and less likely to leak. This single geological layer made the entire project possible. To meet under the sea with extreme accuracy, surveyors built a precise underground reference system. You cannot simply dig and hope. Every centimeter matters when the goal is to meet another tunnel coming from the opposite country. And this is not 1 tunnel. It is 3 tunnels, working together as 1 system. The Channel Tunnel is actually 3 tunnels running side by side. 2 large tunnels carry trains in each direction. Between them is a smaller service tunnel. This middle tunnel is the lifeline of the entire system. It exists for access, maintenance, and emergency escape. A tunnel is not just a hole. It is a moving factory underground. You need electricity, ventilation, transport systems, concrete segments, and non-stop removal of excavated material. If any part stops, the whole operation freezes. The first step was building the tunnel entrances, called portals. On the French side, engineers dug a massive vertical shaft at Senget. This shaft allowed tunnel boring machines to reach the correct depth and begin their journey toward England. The real hero of this project is the tunnel boring machine, or TBM. It is a moving underground factory that cuts rock at the front while building the tunnel behind it. At the same time, Phase 1 focused on control. Engineers first launched the service tunnel. This smaller tunnel acted as a scout, checking ground conditions before committing to the larger train tunnels. It warned engineers of trouble before it became dangerous. As the TBM moved forward, it installed concrete lining rings every few meters. These rings lock the ground in place and block water from entering. Behind each ring, grout was injected to fill empty spaces. No gaps were allowed, because water is always searching for a path. Everything the machine cut had to be removed. You do not dig a tunnel, you move a mountain, 1 conveyor belt at a time. If spoil removal stopped, the entire tunnel factory stopped with it. Alignment checks happened constantly. Drift too far, and the machine could hit unstable ground or miss the meeting point entirely. Even in good geology, small water leaks appeared. Pumps, drains, and inspections kept everything dry and controlled. Fresh air was critical. Ventilation ducts pushed clean air forward and pulled dust and fumes back. Every shift began with safety checks, gas monitors, lighting, communications, and escape planning. This was high-risk work with no shortcuts. Some sections required carving out large underground caverns. These spaces housed crossovers, equipment rooms, and systems that would operate for decades. Thousands of identical concrete segments were needed. This was precision manufacturing, not guesswork. Now the real race began. Multiple machines from both countries, aiming to meet under the sea with near-perfect accuracy. Both Britain and France launched tunnel-boring machines toward each other. Every machine followed a carefully calculated path. In some areas, the ground was harder to control, especially on the French side. Engineers managed pressure at the tunnel face like a submarine bulkhead. Speed mattered, but accuracy mattered more. Fast digging was useless if the tunnel line was wrong. Engineers constantly rechecked the tunnel's position and shape. Under the sea, there is no second chance. As digging continued, engineers planned cross passages. These passages connect the rail tunnels to the service tunnel. They are critical for evacuation and maintenance, both now and forever. Trains push air like pistons when they move. Pressure relief ducts were built so air could flow safely, preventing discomfort and danger for passengers. The service tunnel became the backbone of everything moving: people, equipment, and rescue teams. Waterproofing depended on details. Gaskets, bolts, and perfectly shaped rings had to stay sealed under constant pressure. Any leak was treated immediately. Small problems were acceptable only if they were controlled early. This entire operation ran like a relay race. Machine after machine, crew after crew, keeping pace, keeping alignment, and keeping calm. No drama, just discipline. The service tunnel reached the meeting point first. A small opening marked a massive achievement. Two countries were now connected under the sea. Engineers did not celebrate immediately. They measured. Alignment mattered more than applause. Next came the main rail tunnels. These openings were larger, louder, and riskier. Hundreds of cross passages were built, making the tunnel survivable in emergencies. The service tunnel remained the protected escape route. Crossovers allowed trains to switch tunnels when needed. Think of them as underground interchanges. Once excavation ended, the project shifted from digging to building a railway. Surfaces were finished for cables, lighting, and walkways. Railways demand extreme precision. Even small geometry errors can cause problems at high speed. Walkways were added so crews could safely inspect and maintain the tunnel. Power systems, communications, sensors, and lighting turned a concrete tube into a controlled transport system. Redundancy was everywhere. If one side lost power, the other could keep essential systems alive. Digging the tunnel was only half the job. Making it safe, reliable, and controllable was the real challenge. Rail systems were installed with tight tolerances. Smooth alignment was essential for trains traveling at high speed. Overhead electrification delivered power, with almost no margin for error due to limited space. Signaling and automatic protection systems were critical. At over 200 kilometers per hour, surprises are unacceptable. Communication systems linked trains, operators, and control centers without interruption. Ventilation systems were designed not just for comfort, but for emergencies. Smoke control, heat management, and pressure balancing were all planned in advance. Drainage and pumping worked constantly in the background, quietly fighting water. Fire protection systems were layered. Water supply points, compartment doors, and procedures guided passengers into the service tunnel during emergencies. This was submarine thinking applied to rail transport. Everything reported to a central control center: trains, power, airflow, alarms. Decisions had to be fast and correct. Systems were tested together, not individually. The tunnel had to work as one machine. Before opening, engineers walked every section. They tested failures in their minds. In emergencies, minutes are everything, and timing was measured down to seconds. Testing began slowly. Trains ran at low speed. Engineers listened for vibration, watched air movement, and checked clearances. Then speed increased. Air pressure became a system-wide test. They rehearsed abnormal event stops, communication failures, ventilation changes, and evacuations. The rule was simple. Passengers always move into the service tunnel, never along the rail tunnel. Run after run, systems were pushed until results became boring. Boring meant reliable. The tunnel was shifting from construction to operation. Once open, the tunnel became an everyday machine. Passenger trains, vehicle shuttles, and freight all moved on strict schedules. Freight turned the tunnel into an economic artery, moving heavy loads between countries. Maintenance happens when passengers sleep. Crews inspect rails, power lines, and systems daily. Small issues are fixed early to prevent big failures later. Water management never stops. Pumps, drains, and sensors are checked constantly. Safety is not a what I'm designed, it is a habit. From above, you see nothing. Beneath the channel, a massive system works every day. Two portals, one invisible link. Trains pass under the sea as if it is normal land. That is the real achievement. This tunnel turned borders into schedules. For passengers, it feels simple. For engineers, it represents decades of learning, precision, and discipline. Surveying, geology. 3 tunnels, TB-MIS, concrete rings, cross passages, pressure control, rail systems, constant monitoring. All of it disappears once the train starts moving. The Channel Tunnel is built like a submarine and run like a railway. It works because crews treat it as a living system every single day. That is the legacy. Not drama, not spectacle, just a train running safely under the sea, again and again, as if it has always been there.